you very much.
Thank you. I want to thank the organizers for this opportunity. So in the next 15 minutes or so, I will talk about our new tool, time-aware RNN, to analyze electronic health records data. We had some results on Alzheimer's disease as well as mortality prediction using the MIMIC-3 data set. I want to say upfront, so this is Serdar Bozdag. The first author, Mohammed, my PhD student, couldn't make it due to visa issues, but he did a really great work. This code is available on GitHub, and we encourage you to use it, and it can be applied to other type of EHR data sets. So I think for this COSI, I don't need to explain too much about electronic health records, but we can say that electronic health record is pervasive. It's everywhere. It's available, and machine learning and deep learning methods could be utilized, especially for early detection of diseases, and that's going to be helpful for patients, their caregivers, as well as the healthcare system. To prevent diseases before they occur. And it's been done. There are several applications of traditional machine learning methods as well as deep learning methods on EHR data. We just discussed one talk about that just a few minutes ago. Traditional machine learning models have the issue with dealing with the time series, longitudinal EHR data. So if someone has several visits to the clinic, and we have this longitudinal data, then like the random forest model, for instance, might need to just maybe look at the aggregate data or the most recent data, or you have to concatenate all those data, but it's hard to extract the temporal relations. For that, recurrent neural network methods or transformers have been used extensively, but the issue with RNNs or transformers is the interpretability of the results. So you get some results, but it's kind of hard to explain why this prediction is done, what are the important features. Another issue is EHR data is some data analysis challenges. One of them is the intervals between the clinical visits vary from one patient to another. Like in this example, you can see one patient visits the doctor in short intervals and then doesn't go to the clinic for maybe 1 year. So RNN, which was first implemented on natural language processing, where you just analyze the words in a sentence, you just assume that each consecutive word has equal distance between them. But for EHR, that's not the case. For EHR, the difference makes an issue, and vanilla RNN methods cannot handle that. There are methods for that, and the question is, how can we predict particularly future clinical outcomes by addressing these irregular time intervals, as well as making these models interpretable? There are some methods for that. TLSTM is one of the RNN-based methods where the time difference between consecutive visits are integrated to the model. Last year, we presented PPAT at ISMB, and that's also a model where we integrate the age of the patient at the time of the visit as a way to integrate, embed this time difference between consecutive visits. In terms of interpretability, there is retain, which computes some attention values at the feature level and the visit level, and which can be used to interpret the results. In this work, our contribution is two deep learning architectures, time-aware RNN and time-aware RNN autoencoder. The first one is utilized to predict the diagnosis at the next clinical visit. So we have this time series longitudinal EHR data. We train based on, let's say, first 5 visits, and we want to predict what would be the clinical diagnosis at the next visit, at visit 6. And for the autoencoder model, we would like to predict the visit at the future. like, again, we train on 5 visits, but we want to predict what would happen at visit 8, for instance. And we had a time embedding layer in this architecture, which handles the varying intervals between consecutive visits. And we had a dual level attention mechanisms to make the model more interpretable. We have the QR code for the GitHub page, so the code is available, and the full details are in the paper, but I'll give a brief overview of the architecture. So this is the architecture of the first model, TA-RNN. So what you see here is we have a time embedding layer, which gets the raw EHR data and the elapsed time between the consecutive visits, and then creates a latent representation, which goes to the attention-based RNN, and which creates a context vector, which is further latent representation. And then we aggregate the tabular demographic data, if it's available, some maybe confounders, and we feed them to a downstream machine learning model. Here we use MLP, multi-layer perceptron, and then at the end we make the prediction. So if we zoom in to the time embedding layer is actually very simple. So we have the raw expression data, and we have this elapsed time between consecutive visits. It could be in terms of hours or in terms of days. The unit could be different. So with that elapsed time, we're using the transformer's positional encoding function, like inspiring from there. We use this function to convert this data to time embedding data. And we concatenate that with the raw expression data to create the new representation. So Z integrates the interval information between consecutive visits. Then goes to the attention-based RNN model. Over there, this is RNN, but we compute 2 attentions, like in the retain method. We compute attention at visit level. We would like to know, among those visits, which visit was the most important. So we compute an attention value for each of the visits. And we also compute attention for each of the features in that particular visit. So the visit is a vector. We have 6 visits, so 6 scalar values. Feature is a matrix because for every visit, we have a bunch of features. And we combine all of them with the visit level and the feature level. Attentions are combined with this Z, which gives us this context representation from the RNN. And that goes into the MLP with demographic data, and we get the prediction. So the autoencoder version is same as TA-RNN. The only difference is at this stage. So it's the name implies it's the autoencoder. So once we have C, this context, what we do is we create the next visit data in an autoregressive manner. Like, again, I'm using maybe 6 visits to train, and I want to predict what would happen at visit 9. So what I do is I predict what would happen at visit 7, 8, 9, just using the decoder, and then use that to predict what would happen in the 10th visit. So, and this can go as long as you want. There is no limit how future you want to predict. And again, at the end, you add the demographic data and make the prediction. Okay. And the loss function also, we make the loss function a bit customized. So we want to give a little higher priority to the recall. And the reason is here we want to do early prediction of a disease. And if the disease would occur, we would like to predict that. If the disease wouldn't occur and we make a false positive prediction, it's okay, especially for the Alzheimer's example that I'm going to give. If we tell someone that you might have dementia in the future, that person will maybe change their lifestyle, maybe do more exercise, maybe do crossword puzzles or whatever they want to do, and to try to prevent. But the other way around, if it says someone, you're good, you're not going to convert the dementia, so it's a false negative, then they might be just relax, and then that conversion would happen. So we want to emphasize the recall more, and we make the loss function customized for that reason. So we had results on 2 separate prediction tasks, but for the interest of time, I'm just going to talk about the Alzheimer's disease example. The other one, you can check the paper. So here we're trying to predict the progression of Alzheimer's disease. And here's a bit of background on the problem. So Alzheimer's disease has an intermediate stage called mild cognitive impairment. So these people also have memory issues, but they can still do their day-to-day activities. Some of those MCI, mild cognitive impairment people, would convert to AD eventually. Some don't. So we call them MCI converter and MCI non-converters. And we would like to detect who would convert to AD before that conversion happens. And we would tell them you would maybe become Alzheimer's. So maybe use some FDA approved drugs or do something to at least be prepared. So that's the goal of this prediction task. We use 2 publicly available data sets, ADNI and NACC, and we use longitudinal cognitive measurement data as well as neuroimaging features, as well as some cross-sectional demographic features. Okay, so we had 2 architectures. One was predicting at the next visit, and the other was predicting at future visits. So predicting at the next visit, we used TA-RNN, and we had multiple scenarios. One was just train on 2 visits and predict at the 3rd visit, or train on 3 visits and predict at the 4th visit, so on and so forth. So we had 4 of those examples. And in terms of comparison, we use traditional ML methods, RF, random forest support vector machine, as well as TLSTM and PPAT. And here are the results. This is F2 score, and the green one is our method. PPAT is our previous method, and these are the other state-of-the-art or the traditional baseline methods. And for almost all cases, except for one case, our method outperforms the other methods. There was a statistically significant difference with TLSTM and other methods for most cases. With PPAT, their performance is very similar, but our advantage is that PPAT is not interpretable. We use SHAB on the PPAT results to be able to explain the results. Here we have attention values. We have a more deeper interpretation of the results. So that was the advantage. For the future visit predictions, we use the autoencoder version of it. And again, here the scenario is we use 2, 3, 5, or 6 visits to train. So 4 separate scenarios. And then we predict at the 2nd, 3rd, and the 4th visits ahead. Okay, so there are many results because for each of this training, we do 3 separate predictions. And here's one of these results. If you look at the top left corner, this is the model that is trained on 2 visits only. And then here we are looking at visit 4. And then here we look at visit 5 and visit 6 prediction. And again, our method outperforms other methods for most of the cases. When we train on 3 visits and 5 visits and 6 visits, we have a similar trend. We also did an ablation study where we disabled some of the modules in the architecture. We disabled the attention module, and we also disabled the time embedding module. So A-RNN is only the attention is there. We don't have the time embedding. And T-RNN is time embedding is there. We don't have attention. So as you can see, when we don't have the time embedding, there is a drop in the performance. I mean, clearly the performance is, and the last row is our proposed method, TA-RNN. But TA-RNN, when we don't have the attention, sometimes it did even better. I mean, slightly better than our own method. I mean, it's not significant, but still slightly better. So when we don't have the attention, we lose interpretability, but we might do a little better, but not always. But if we don't consider the intervals between consecutive visits, then we saw a significant drop in the performance. And how much time do I have? Okay, so that's going to be enough for me to talk about the interpretation of the results. So now we have those attention values. We visualize those attention values to be able to shed light on what were the important visits and the features. Here, for these plots, we are focusing on the model that was trained on 6 visits. And what you see is that these are the patients on the test set. And these are the visits, and those are the attention values. So the brighter the color means more attention. And what we see is the 5th and the 6th visit has the highest attention, which makes sense because as you get closer to the recent time, it gets more important. And for the features, again, these are the features that we use, and these are the same patients and the attention values. Again, the brighter means more attention, and we had like CDR-SB, MMSE. All of those are cognitive tests, and I mean, it's not surprising that those test results are very important. The model gave a high attention to those because at the end of the day, clinicians also rely on those tests and other things to make the diagnosis. And when we look at everything as a kind of an average, so we can see that, again, the attention value of the visit 6 gets higher. Visit 5 is high. The other attention values were low. This is overall, these features are important. And if we combine these 2 plots in an element-wise manner, this is the picture that we get. Like those features at the very last visit gets more and more important. Okay, so with that, I like to conclude that we proposed 2 deep learning architectures, which utilizes the intervals between consecutive visits in EHR data to predict the diagnosis. We showed results on Alzheimer's disease. We also had some results on mimic data sets, and we hope that our method could be utilized for other EHR data sets. We make the code available for community to utilize and let us know if they need help with anything. We made the models interpretable with attention values, and we hope that these would also give more confidence for clinicians or for biologists to understand the results. With that, I'd like to thank my group, particularly Mohammed, who published PPAT last year and then TA-RNN this year, and he's going to be on the job market next year. So keep an eye on him and our funding sources. Thank you.
I have a quick question. So this is domain disease agnostic. You applied to Alzheimer's disease, for example, can be expanded to Parkinson's disease also? And I have a couple of other questions. But
sure. So I can repeat the question. So the question was, and thank you for this question. So is this method a disease agnostic method? So it is disease agnostic, and to be able to demonstrate that, we use mortality prediction using the intensive care unit data from MIMIC, as well as Alzheimer's disease data. Actually, my funding is from NIGMS. This is General Medical Science, and we make all of our methods disease agnostic because we don't want to. We want to make methods that could be applicable for various diseases. Yeah.